what we the topic of hashing, and then we'll move on to the next topic here, which is probabilistic algorithms. Okay. So again, we use hashing because it gives you excellent average case. Okay. And what is a typical alternative for hashing? Typically, you talk about binary trees. Right? So binary trees will give you log n, order of log n time for insert, retrieval, and all kinds of operations. So a typical alternative for hashing is binary trees. But generally, binary trees tend to be more expensive in practice because you end up having to follow multiple pointers, and as I told you, pointer chasing is quite expensive on today's processors, so it's not often giving you very good performance. And in addition, when you have to have balanced binary trees, right? So you get log n only if you have the trees balanced, and balanced binary trees that requires more overhead. So between the additional overhead and the fact that you have to chase pointers, generally hashing is often wins out. Okay, but of course, the downside of hashing, which is why we are spending so much time on it, is that things could clump up. There could be lots of collisions, and then your expected fast performance ends up being extremely slow. Right? So that's why we really pay attention to collisions, and we want to make sure that collisions don't occur, even if regardless of input distribution. Okay, so that's always our goal. How do we get low collision in spite of input not being distributed uniformly, right? So one of the things that we want in hashing is, as we said, right? So there is the set U that we are trying to hash, right? And then that is going to get mapped into a smaller domain, right? So this domain is, let's say, 0 to some n, right? So we want to map the universe of objects we want to hash into a small range so that we can use the range as an index into an array, right? So what are obvious ways to do this mapping? One is, well, I can just divide, right? So I can, let's say this U, if I multiply an element x over here by actually the other way, right? So if I scale, well, that's one way to do the mapping. It's obviously a very poor way to do the mapping, because what happens is that if I have 10 elements over here, they will get mapped into a much smaller number of elements there, and therefore you'll get guaranteed collision quite often, right? So it's definitely not what you want. The other approach is, what we often talk about, at least you take a modulo using the space. Okay, so if you use the modulo, then at least if you have, some range over here, that will get mapped to some range over there, right? So what happens is that, well, okay, you didn't really necessarily make very good use of the range of the hash table, but at least you didn't make any things much worse, right? If you just took some kind of mod of the value that's there, right? So we just said we're just going to do x mod n, right? Now, again, our goal is that regardless of how the input is distributed, right? So in this case, what I'm saying is that even though the input could be over this entire range, it turns out that the set of elements that you are given happens to fall in that small range, right? So what we want in the hash table is that regardless of how the input is distributed, we want to kind of use the entire range over here, right? If it's uniformly distributed over this range, then we will have a much better properties in terms of not having too much clustering, not having too many collisions, and so on. Right? So that's what we want. We want somehow, no matter how small or in what manner the points are distributed in the original domain, we want them to be somehow scattered over here, right? And this is often why you always see that we multiply points, right? So if, let's say you multiply so there is one function we talked about last time, which was Rx mod n, right? Where R is a number between 0 and n, right? Or 0 and n minus 1. If you multiply by that, then what's going to happen is that even points that are successive over here are going to get distributed far apart, right? So if you have x and then x plus 1, right, when you multiply by r, this is going to become rx, and this is going to become the point rx plus r, which means that it's going to be this far from the original point, right? So you have this scattering effect. You have a small domain. If your points happen to fall within a very small range of your input domain, even then the multiplication scatters them around so that you don't have the same kind of clumping over here. Okay, so this is why often you'll see that most hashing functions are using operations like multiplication to scatter the points. And that's when the problem comes, because when you try to scatter them, then maybe you scatter them in a way that causes too many collisions. Okay, that's why we want to think about not only the fact that you're scattering, but also what could happen after you apply the operation and whether you end up having too many collisions. Okay, and then we talked about, okay, so in the basic case of multiplying by r, we have sort of a one-dimensional case, right? So your universe is this one-dimensional. Your target is, always one-dimensional, right? So in the case of if you have a string, then we can think of string as a vector, right? Where each character, is like a coordinate in space, and so your universe then becomes sort of a multi-dimensional space, and you could still have the same kind of, behavior in terms of how points could be all clustered around, one small part of the space, and you again want some way to explode them out and spread them out in this target domain, right? And once again, we talked about how you could use, again, multiplication and summation, right? So we said Ri, Xi, you do a summation where Ri is a random number for the ith dimension, and you add them up. Well, that gives you another hash function, and we said that also gives you this universality property. So, that's what we want from hash functions and universality. Then we also talked about perfect hashing, which basically is a way to ensure that you don't have any collisions at all. And it's possible to do that. In practice, though, you might not get a lot of benefit, because what's the difference between 1 and 2? If let's say on the average you're going to get one collision versus 0 collisions, maybe it doesn't make a lot of difference. But on the other hand, if you have an application where you need predictable performance, and then you want for each operation you do, it shouldn't take an unpredictable amount of time, well then perfect hashing is an option, because then you have that predictability. Okay, so now we'll talk about